Well, in this lesson we're going to learn about chain rules. Chain rules, not the chain gang, but for functions of several variables. And theorem 13.6, chain rule for one independent variable. Well, if w is a function of x and y, where f is differentiable function of x and y, and if x is another function of some third variable t, actually maybe fourth, and y is also a function of t, where g and h are differentiable functions of t, then w is a differentiable function of t, and the derivative of w with respect to t is the partial derivative of w with respect to x times dx dt plus the partial derivative of w with respect to y times dy dt. Note the dx dt, the dy dt, and actually the dw dt, they're not partial, they're derivatives. And dw dx, dw dy, they're partial because they're going to be the derivative of this function of two variables, x and y, with respect to x and y respectively. So here's a chart making a picture of it. Like, you start with a variable t, dx dt, and then w is a function of x and y, so therefore we need a dy dx and a dy, or dw dx and a dw dy, and y itself has another variable, a derivative, dy dt. I'm not sure if this is real useful, but it does kind of describe how to find such a derivative. Anyway, same approach works for functions of three variables. So, and I will show you both ways of calculating dw dt. First, I'll use substituting everything back and making it a function of one variable only, and then I'll use this idea and show that they're the same. So let w be f of x, y, z, and let that be x times y times cosine of z, and let x be t, y be t squared, z be arc cosine of t, and so what we have is three different variables, each of which is a function of t, and w is a function of our three variables. So first way is substitute, so w is a function of t. So substituting for x, we just put a t. Substituting for y, we put a t squared, so now we're up to t cubed. Substituting for cosine of z, well, z is angle whose cosine is t. So what is the cosine of the angle whose cosine is t? Well, just t. So we have t times t squared times t, so t to the fourth. W is t to the fourth. Find the derivative of that. What could be easier? 4t cubed. The other way. It's a little drawn out, and this would be the formula if you had three variables. Dw dt is y times cosine of z, and what is that? Well, that's the partial derivative of this with respect to x. See, because y and cosine of z would be considered constants. Times dx dt, well, the derivative of x with respect to t is just 1. The partial of w with respect to y, again, y is a constant. I'm sorry, x and cosine of z are constants, and they're multiplying y, so we got just x times cosine z times the derivative of y with respect to t, so that would be 2t, and then plus partial of w with respect to z. Well, that's where we're going to actually have something go on here, because the derivative of cosine is negative sine. X and y are both constants, so we would have x times y times negative sine of z, but now we're going to also say the derivative of the angle whose cosine is t. And that might or might not be very straightforward, but it is this particular, it's negative 1 over square root of 1 minus t squared. I could do a little sidebar and show you why that's the case. Because see, if z equals arc cosine of t, then we'd have to say therefore cosine of z equals t if we differentiate both sides with respect to t. We get derivative of cosine is negative sine, so negative sine z times the derivative of the inside function, which is dz dt, is equal to 1. So dz dt equals negative cosecant of z. Well, now that's tricky. So how are we going to figure that one out? Well, we need a picture. Well, for my sidebar here, since dz dt equals negative cosecant of z, and we know that cosine of z equals t, so actually I wrote a theta here. I guess I probably should have written a z. Cosine of this angle z is t, so that's t over 1, but that means the opposite side would be the square root of 1 minus t squared. So therefore the cosecant of this angle, I know I called it theta, I should have called it z, but I'm not going to fix that now. The cosecant of z is hypotenuse over opposite, and it says take the negative of that, so it's negative 1 over square root of 1 minus t squared. So that's where this came from. Substituting, well, y, I'm thinking back, y was equal to t squared. Cosine of z would be the cosine of the angle whose cosine is t, well that's just t, and then times dx dt, well that's just 1. Oh, I already went through that. Sorry, me being dumb. So we got t squared times t times 1, 2t cubed here. We've got t times t squared, and here we have the negative of this over itself. That would cancel out, and I think you can see what happens. We have a t cubed here and a 2t cubed here, and if you cancel the signs, we got another t cubed here. Cancel the signs and cancel the radical. So we wind up with 4t cubes, which is just what that derivative is. Now, I'll be honest, this was my method of choice, but I did want to show you that that theorem works out nicely. I needed this diagram to compute sine of the angle whose cosine is t. That was for here. That was similar to the drawing I made over here. I guess it was really the same drawing. So the sine of the angle whose cosine is t is opposite this over hypotenuse this. So that's where this came from. And notice how nicely this and this canceled out, giving us a positive t cubed here, which led to all 4 t cubes. Enough.